the issue of BIBO stability is two things. Either in the pole zero domain, it's BIBO stable if all the poles are inside. If any of the poles are outside, it's not BIBO stable. And in the time domain, it's BIBO stable if you sum up the magnitude of the impulse response. If it's finite, then your whole system is stable. And if you sum up the magnitude of your impulse response and it's not finite, then your system is not BIBO stable. BIBO stability. So BIBO stability is talking about the stability of a system. It's not a particular input. It's if we have any kind of input that goes into our system, it would be really nice to know if the system will ever blow up. We can make any system blow up, even a perfectly stable one, if we allow our input to go arbitrarily big. If our inputs have infinities in them, then even a good, well-behaved system will have outputs that go to infinity. So what BIBO stability is saying is that if our input is bounded, could be bounded by a lot, but it doesn't go up to infinity or down to negative infinity. If every single possible bounded input guarantees a bounded non-infinite output, then we call it BIBO stable. So it's literally bounded input gives you a bounded output. And that's where the name comes from. Some systems that you might think are perfectly reasonably well behaved may not be BIBO stable. And I'll give you an example of one. If your H of n is a step, for instance, this is the block diagram of your system. Your input goes along and gets summed with the previous output. This has an impulse response of U of n. Why is that? If you put in an impulse in here, then that impulse causes a 1 out at first, but then the next is it's delayed that 1. So it puts out a 1 in the next, and then it puts out a 1 in the next, and it's always putting out 1. So for this, an impulse in gives you a step out. We would say its block diagram looks like this. And if its block diagram looks like that, we could describe it in the z domain as being the transform of our u of n, which we know as 1 over 1 minus z to the negative 1. This seems like a perfectly well-behaved system, but in fact, it is BIBO unstable. If you were to feed this a u of n in, what you will get out is a u of n has this transform multiplied by this transfer function, gives you a n u of n output. So let me just make it clear. This is a different kind of input, and this is the corresponding output. And this has no bound. Your input is bounded. It's never greater than 1. Your output is unbounded. No matter what number you choose, a million billion, I can tell you a time at which it reaches that. Answer is n equals a million billion. So not all reasonably nice looking systems are BIBO stable, but you want to know if a system is BIBO stable because, for instance, if it's controlling a plane, you want to know if reasonable inputs from your stick might ever cause the plane to have an arbitrarily large deflection in space. There's two ways to tell that. The first way to tell if it's BIBO stable, the first way to see if a system is BIBO stable is, I think, very intuitive, and it's to say, hey, listen, we know that the output is the convolution of the input with the impulse response. So if our impulse response, if there's no way that when we sum our impulse response, if there's no way that that impulse response can sum to infinity, then no coefficients of our input when convolved with our impulse response could be summed to infinity. So as long as our impulse response's sum is finite, then it's BIBO stable. And alternatively, if it's equal to infinity, then it's not BIBO stable. And there's another way to tell if it's BIBO stable or not. And that's to take a look at this demonstration that I wrote. Every single pole corresponds to a power series in the output. When we draw our h of z, no matter what our numerator is, there's our first pole, and there's our second pole, and so on. And these are all poles that we could draw in the complex plane. Whatever lambdas these are, we can draw like this. When we want to find the output, because it's equal to our input times in the frequency domain, our transfer function. Every single pole, every single part of this denominator in h of z will also appear in our y of z because we're multiplying them together. So in other words, we know that our y of n, when we inverse transform it, will have something that looks like that pole raised to the n plus our other pole raised to the n plus our other pole raised to the n plus, and there might be a bunch of other poles that come from our input. But if our input is guaranteed to be BIBO stable, then all those poles are guaranteed have a magnitude of less than 1. But if any of these guys have a magnitude greater than 1, if say lambda 1 was 2, then you can see how if this was 2 raised to the n, this would grow arbitrarily large. And that would come from a lambda in the frequency response being 2. And in fact, any one of these lambdas whose magnitude is greater than 1 will cause it to go unstable. So the other way of talking about is its system BIBO stable in the frequency domain is saying the magnitudes of all of the poles strictly less than 1. And if they are, it's BIBO stable. And if any pole has a magnitude greater than 1, then it's not BIBO stable. And that's what you saw in this demonstration that said the moment that any of these poles go outside the unit circle, all of a sudden we can see in the time domain, it quickly blows up. And that's true no matter where it is outside the unit circle. And the closer it gets to the unit circle, the closer it gets to not being BIBO unstable. You can kind of see that right here. This is high frequency. And if we bring it in, come on. If we bring it in, everything nicely decays. I'm going to get rid of that. If we bring it in, everything nicely decays. If we put it on the unit circle, it actually just stays at the same value constantly. Then as we bring it out, it gets arbitrarily big. I'm going to take out these guys to make it scale better. Now you can really see how high frequency in quickly decays as we get it closer and closer to the unit circle. It's not decaying as fast. Now it's barely decaying at all when it's on the unit circle. It just doesn't decay. It just stays right there forever. And the moment it just goes outside that unit circle a little bit, now it's starting to grow unbounded. And instead of having it at the highest frequency possible with alternating, we could do it over here. And now it's going to be every other. Now we have this intermediate frequency, but it's the same thing. Here it decays. We put it right on the unit circle and it just stays constant. We bring it outside the unit circle. We can see it increases. Same thing for low frequencies. Here's omega equals 0. It decays, gets closer to the unit circle. It decays more slowly on the unit circle. This is the transform of a pole at 1 is the transform of 1 over 1 minus z to the negative 1 is the transform of a unit step. And that's what we get out is this unit step and bring it right outside there. And now no longer is it a step, but now it's multiplied by some coefficient times n. Okay. So the takeaway there is that there's exactly 2 equivalent criteria to see if a system is BIBO stable. One is, can you sum up the magnitude of its impulse response and have it less than infinity? And the other is that are all the poles have a magnitude less than 1? In graduate school, you'll discover that if you're dealing with systems that are not causal, then this is still true, but the bottom condition switches to are all the poles greater than 0? Because now instead of these things being raised to the n power, they'll all be raised to the minus n power. Okay,